Hello, my name is Robert Smith, and I'm with New River Community College. And today we're looking again at the solubility product and the solubility equilibria of salts. So we're asked to calculate the solubility of calcium phosphate, and we're given that its solubility product, which again, remember, that is KSP of 1.2 times 10 to the minus 26. So first we want to create a reaction of calcium phosphate in solution. So the equation for calcium phosphate will be Ca3PO4 2. Okay, and when it's in liquid, depending on the rate of saturation, it'll have 3 calcium 2 plus 2 PO4 3 minus. Okay, so that's our reaction. And we know KSP is 1.2 times 10 to the minus 26. If we note that this is solid and we did an ice table, we could say that we're not even worried about this side, but this side starts at 0 and 0. After we've done that, we need to add 3s to the calcium and 2s to the phosphate. That's because we're carrying down the coefficient. That's standard practice. So our calcium is 3s and our phosphate is 2s. So that's just like an ice table, except for equilibria, solubility equilibria. Okay. And so when we calculate our KSP, which, I mean, normally if we set up this KSP equation, again, it's products over reactants. So we're going to take 3s for our calcium. And remember, we have to raise it to the power of the coefficient. So it's 3s cubed. And similarly for phosphate, it'll be 2s squared. And if you FOIL everything out or expand all the exponents out, you would end up getting 108 s to the 5th power. Okay, and the reason why we have these their values as 3s and 2s can also be associated with the charge. If you wanted to do a charge balance equation. So you have your calcium 2 plus is equal to phosphate 3 minus. But in order for that to be equal, there has to be 2 phosphates and 3 calciums, right? Because then you have a plus 6 on one side and a minus 6 on the other side. So that works. That's just a sanity check on what we're doing. Then we can plug in our KSP value. So we have 1.2 times 10 to the minus 26. And that's equal to 108 s to the 5th. Dividing by 108 and then taking the 5th root or raising it to the 1/5 power, we find that s is equal to 2.6 times 10 to the minus 6 moles per liter. Remember that the solubility product is the product of the molar solubilities, but we're not asked for the molar solubility, we're asked for the solubility. That's maybe a little confusing, but remember, molar solubility involves moles per liter, and solubility will be grams per liter. So calculating that requires us to know what the molar mass of calcium phosphate is, and we do. So we can take 2.6 times 10 to the minus 6 moles per liter, and multiply it by 310.18 grams per mole. The moles cancel and we're left with grams per liter, which will be approximately, keeping to the correct sig figs, 8.0 times 10 to the minus 4 grams per liter. And we could even write it in, we can keep it in scientific notation, and that's perfectly fine. Or you can even say that it's like 0.80 milligrams per liter. And that's all there is to it. Thank you so much.